The image arrived slowly, assembled from data collected by radio telescopes scattered across the face of the planet. Each one pointed at the same patch of sky in the faint northern constellation Draco. The signals from each telescope had been recorded. What emerged, after months of careful processing, was the sharpest image ever taken of a particular ring of light in the distant universe. The team had been waiting for it. Some of them had spent years working toward this moment. And when the final image resolved, when the ring appeared on screen in greater detail than anyone had ever seen it, one of the scientists noticed something small. A pinch. Not a gap, not a break. A subtle distortion in the curve of the ring. A place where the smooth arc of light was compressed slightly out of shape, bent inward by something that had no right to be there. The team leader, an astronomer named John McKean, would later describe it in language stripped of drama, the kind of language scientists use when they are trying to be precise and cannot quite contain what they are feeling. A telltale pinch in the gravitational arc. That was the phrase. A telltale pinch. Behind that phrase sat something extraordinary. The ring they were looking at is not a physical ring in space. It is an illusion produced by geometry, a consequence of two galaxies aligned along the same line of sight from Earth, one closer and one vastly farther away, their positions stacked so precisely that the gravity of the nearer galaxy bends the light of the distant one into a loop. It is one of the universe's most spectacular optical phenomena, and it had been known to astronomy for almost 3 decades. This particular ring had been photographed by the Hubble Space Telescope. It had been studied and measured and written about in journals. It was considered well understood. And now, in the clearest image ever produced of it, there was something wrong. The distortion the team was seeing meant that something was bending the ring from the outside. Something with enough mass to warp the path of light passing near it. Something that was not the foreground galaxy, whose effect on the ring had already been accounted for. Something additional, something extra, whatever it was, it sat somewhere near the foreground galaxy, or along the line of sight between us and it, and it was pulling on the ring's light with a gravitational grip that could be calculated precisely from the size and shape of the distortion. When the calculation was done, the number it produced was not small. The hidden object had a mass of roughly 1 million times the mass of the Sun. More than enough mass to be a small galaxy in its own right. 1 million solar masses of matter sitting at a known position in the sky, its location triangulated by the geometry of the distortion with remarkable precision. And it produced no light, not in visible wavelengths, not in infrared, not in radio, not in ultraviolet or X-ray or any of the other forms of radiation that sensitive instruments scan the sky for. The most powerful telescopes ever built had been pointed at its location, and they had found nothing. No faint glow, no trace of starlight, not a single photon that could be attributed to the object itself. By every direct method of observation that humanity possesses, the object does not exist. And yet its gravitational fingerprint is unmistakably there, pressed into the shape of a ring of light that has been traveling toward us for 10 billion years. 10 billion years. That is the distance the light had to travel to reach us. The object is not in our galaxy, not in our cosmic neighborhood, not even in the relatively nearby universe. It sits at a distance so vast that when its gravity last touched the ring's ancient light, the Earth had not yet formed. The Sun did not yet exist. The universe itself was less than half its current age. This is a message from the deep past, a gravitational whisper carried across more than half the age of the cosmos, arriving now as a barely perceptible kink in a ring of ancient light. 1 million solar masses, 10 billion light-years away. No detectable light of any kind, and a shape, because the team did not stop at measuring its mass, They also measured how that mass was arranged inside it, a shape that does not match anything in the catalog of known objects. Not a galaxy, not a typical clump of dark matter, not anything the standard models of the universe predicted should exist. The team had found something. They were not entirely sure what. That uncertainty, far from diminishing the discovery, is what makes it significant. For decades, physicists and astronomers have known that the vast majority of the universe's matter is invisible. They have measured it indirectly in 100 ways. They know it is there. But knowing something is there and understanding what it is are two very different things. The object in Draco, the million solar mass something, the pinch in the ring, is one of the first objects in the universe where the question of what dark matter actually is, what form it takes, how it behaves when it gathers into a clump, can be addressed with real measured data from a real specific thing. The easy answers all fail. The comfortable explanations do not work. And that is the beginning of this story, not the end of it. Because what the team found when they asked what kind of thing could have this mass, this structure, this total and absolute darkness, was that the universe had produced something it was not supposed to contain. Something is bending the light that should not be bending the light. Something that gives off nothing. Something that should not be there. And it has been there, waiting in the dark, for longer than the Earth has existed. To understand what was found in the ring above Draco, you first have to understand what a ring like that is. Not just what it looks like, not just the physics of its formation, but why it exists at all and what it took for the human mind to predict it, recognize it, and eventually use it as the most precise weighing scale in the cosmos. The story begins with a thought experiment and a young physicist who was not yet famous. In 1905, Albert Einstein published 4 papers in a single year that each individually would have secured his place in the history of science. But he was not finished. For the next decade, he worked on a problem that had been nagging at him since his student years, a problem with gravity. Newton's theory of gravity was magnificent. It described the motion of the planets, the fall of objects, the tides of the ocean. But it described gravity as a force that somehow acted across empty space between objects that were not touching, a force that propagated instantaneously, with no explanation for how it actually worked. Einstein suspected that something was deeply wrong with this picture. What he produced instead, after a decade of struggle that he would later describe as the most difficult intellectual work of his life, was a theory that did not describe gravity as a force at all. In Einstein's general theory of relativity, published in 1915, gravity is what happens when mass bends the fabric of space and time. Mass does not pull other objects across space, it curves the space itself, and other objects, following the natural paths through curved space, appear to be attracted toward it. The mathematics of this idea are formidable, but the image that conveys its essence is surprisingly simple. Imagine a stretched rubber sheet, taut and flat. Place a heavy ball in the center and the sheet dips. Roll a marble across the sheet and it curves toward the ball, not because the ball is pulling it, but because the sheet itself is curved and the marble is following the curve. In Einstein's theory, the rubber sheet is space, the heavy ball is any massive object, and the marble is anything moving through that space, including light. And here is the critical consequence. Light travels through space. If space is curved by mass, then light, following the curves of space, does not travel in straight lines near massive objects. It bends. A ray of light passing close to a very massive thing, a star, a galaxy, a cluster of galaxies, will follow the curve of space and arrive at a destination slightly different from where it would have arrived had the massive object not been there. Einstein worked out the precise amount by which the gravity of the sun should bend starlight passing near its edge. And in 1919, during a total solar eclipse, when the moon's shadow made it possible to photograph stars near the sun without being blinded by its glare, a British expedition led by Arthur Eddington compared the apparent positions of stars near the sun's edge with their known positions. The stars had shifted by exactly the amount Einstein had predicted. Within 4 years of the end of the First World War, in a collaboration between British and German scientists, the universe had revealed a new truth about itself. Mass bends light. This was not a metaphor or a theoretical preference. It was a measured fact, confirmed against the sky, repeatable by any team with a telescope and a clear view of an eclipse. Once you accept that mass bends light, a certain kind of cosmic geometry becomes possible. Imagine a source of light, a distant galaxy, far beyond your ability to see clearly. Now imagine placing another galaxy, a massive one, somewhere between you and that distant source. The gravity of the intermediate galaxy will bend the light from the background galaxy around it. Depending on the exact alignment, the bent light will arrive at your location from multiple directions, producing multiple images of the same background source or smeared arcs, or, in the case of near-perfect alignment, something extraordinary. A complete ring of light, the background galaxy wrapped entirely around the foreground, won by the bending of space. Albert Einstein himself worked out the mathematics of this possibility in 1936. In a short paper he described as having little practical value. He calculated that if 2 stars were aligned perfectly, the gravity of the nearer one could focus the light of the farther into a ring. He thought such perfect alignments would essentially never occur in practice, that the geometry required was too precise, too coincidental to ever be observed. He was spectacularly wrong, not about the mathematics, which were correct, but about the frequency of the phenomenon. The universe is vast beyond comprehension, and it contains hundreds of billions of galaxies. Perfect and near-perfect alignments happen constantly, in every direction we look. We call the rings they produce Einstein rings, and the broader phenomenon gravitational lensing. The lensing of light by gravity turns out to be one of the most powerful tools in all of astronomy. It allows astronomers to study objects far too distant and faint to observe directly, their images magnified and brightened by the foreground lens. It allows them to map the distribution of mass in the universe, including the dark matter that makes up most of that mass. And, as Simona Vigeti and her colleagues would realize decades into the study of gravitational lenses, it allows astronomers to detect concentrations of matter that emit no light at all, to find and weigh the invisible. But this insight did not come immediately. For years, Einstein rings were studied as curiosities, as beautiful demonstrations of a profound physical principle, as tools for studying the lensed background galaxy itself. The idea that the precise shape of a ring could be used as a scale to weigh invisible dark clumps embedded in the foreground lens galaxy was a subtler and more ambitious insight, one that required both theoretical imagination and instruments sharp enough to measure distortions almost too small to see. To understand how that insight was applied to one particular ring of light in the direction of Draco, and to understand what it eventually found, you have to know the history of that ring itself. A history that begins not in the modern era of space telescopes and supercomputers, but in a radio survey conducted from the high desert of New Mexico in the waning years of the 20th century. What that survey found, and what it would eventually make possible, starts with a name that contains no beauty whatsoever. The name is JVASB 1938+666. It carries no romance, no mythology. It is a catalog designation, a string of letters and numbers encoding the survey that found it and the coordinates of its position in the sky. The letters reference the JVAS survey, the Joint VLBI Astrometry Survey, a systematic scan of the radio sky conducted in the 1990s. The numbers are a right ascension and declination, a cosmic address pointing toward the constellation Draco, a long, faint winding figure in the northern sky, circling the celestial pole with no particularly bright stars and no famous stories attached to it. If you looked at Draco on the clearest night in the darkest place on Earth, you would see nothing remarkable. The ring is invisible to the naked eye, invisible to any optical telescope of ordinary power. It exists at the level of faint radio waves and carefully tuned infrared detectors, a ghost in the sky that only becomes real when you know exactly how to look. It was first identified as a gravitational lens system in 1997 when astronomers scanning the radio sky noticed that the source at those coordinates had the properties expected of a lensed system. In 1998, the Hubble Space Telescope turned its instruments toward the position and captured an infrared image of what was there. The image revealed an almost perfect Einstein ring, one of the most geometrically precise examples of the phenomenon that had ever been photographed. There, surrounding a bright elliptical galaxy in the foreground, was a complete circle of light, the smeared and bent image of another galaxy located far behind it. The geometry of the system, once it was worked out, was remarkable in its scale and its depth. The foreground galaxy, the one whose gravity does the bending, is a massive elliptical, the kind of large, old, star-rich galaxy that has long since finished its most active phase of star formation. Its light left it roughly 8 billion years ago. It is old by human standards, but it is a recent object compared to what lies behind it. The background galaxy, the one whose light forms the ring, lies far deeper in the universe. Its light left it more than 10 billion years ago, before the Earth existed, before the solar system had begun to condense from a cloud of gas and dust, in an era when the universe was less than a third of its current age. When that light departed, there was no one and nothing in what would eventually become our solar system to receive it. And yet, it arrived. It traveled for more than 10 billion years through the expanding universe, and somewhere along that vast journey, it passed the foreground galaxy, whose gravity gathered it from multiple directions and shaped it into the ring that the Hubble telescope photographed. Two galaxies, at two completely different distances, one 8 billion light-years away, one more than 10 billion, their light woven together into a single image by the bending of space. A photograph of JWST 1938 plus 666 is not really a photograph of two objects. It is a photograph of a geometry, a record of how two galaxies happen to align themselves across the depth of the cosmos and of the curvature of space between them. For more than a decade after its discovery, the ring was studied mainly as what it appeared to be, a particularly clean and beautiful example of a gravitational lens. It was used to study the background galaxy, whose magnified image allowed astronomers to examine a galaxy at 10 billion light-years in far more detail than would otherwise have been possible. It was used to study the foreground galaxy, whose mass distribution could be inferred from the precise shape of the ring. It was, in the language of the field, a textbook example. But in 2012, an astronomer named Simona Vighetti and her colleagues recognized that JWST 1938 plus 666 could be used for something far more ambitious than what had so far been attempted. The key insight was this: the shape of an Einstein ring is not determined just by the large-scale distribution of mass in the foreground galaxy. It is determined by every concentration of mass along the line of sight, no matter how small, no matter how dark. If there were a clump of extra mass somewhere in or near the foreground galaxy, a concentration of matter that emitted no light but still had gravity, that clump would produce a tiny distortion in the ring, a slight deviation from the perfect arc that the foreground galaxy alone would produce. By measuring the shape of the ring with sufficient precision and comparing it to what the galaxy alone would produce, you could detect the presence of that extra clump. You could weigh it. You could characterize it. Without ever seeing it directly, without detecting a single photon from it, you could know it was there and know how much it mattered. Veggetti's team applied this technique to JWST 1938 plus 666 and found something. A dark clump embedded in or near the foreground galaxy, with a mass comparable to that of a small satellite galaxy of the Milky Way. Hundreds of millions of solar masses of something that emitted no detectable light, found entirely through its gravitational effect on the shape of the ring. It was one of the first times in the history of astronomy that a dark object at cosmological distances, billions of light years away, had been detected purely through its gravity. It was a proof of concept. It demonstrated that the technique worked, and it raised, with quiet urgency, a question that would take more than a decade to answer properly. The 2012 clump was large, as these things go. Hundreds of millions of solar masses. The theories of how the universe is structured predict that dark matter should gather into clumps of all sizes, ranging from the mass of large galaxies down to objects far too small to have ever formed a single star. The smaller the clump, the subtler the distortion it produces. To detect the smaller objects, you would need an image of the ring far sharper than anything that had been achieved. Far sharper than Hubble could provide, far sharper than any single telescope on Earth could produce. There was a technique that could, in principle, achieve the necessary resolution. A technique that had been producing extraordinary images in radio astronomy for decades, but had never been applied to this particular problem with this level of precision. It was a technique that turned the entire surface of the Earth into a single vast telescope. And when it was finally turned toward the ring in Draco, what it found there changed what was possible. There is a fundamental limit on how sharply any telescope can see. It is not primarily a matter of the quality of the mirrors or the sensitivity of the detectors. It is a consequence of physics built into the nature of waves. A telescope's ability to resolve fine detail, to distinguish two closely spaced objects as separate rather than blurred into one, depends on the ratio between the wavelength of the light it collects and the diameter of its primary mirror or dish. Larger telescopes see more sharply. This is why astronomers build ever larger instruments, why the mirrors of ground-based observatories have grown from inches to dozens of meters, why space telescopes are designed with the largest apertures that rockets can carry. Every increase in size is an increase in the precision of what can be seen. But there is an idea, developed in the 20th century and now at the heart of some of the most powerful instruments in astronomy, that escapes this constraint in a remarkable way. You do not need a single enormous telescope. You need multiple smaller telescopes spread across a great distance, connected to each other, their signals combined, so that they behave as if they were a single instrument as large as the space between them. This is the principle behind interferometry, and it has been practiced in radio astronomy since the 1940s. The signals arriving at two separate radio dishes, if combined correctly, interfere with each other in patterns that reveal the fine structure of the source. The effective resolution of the combined system is not determined by the size of either individual dish, but by the distance between them. In principle, there is no upper limit on how far apart the two dishes can be. And that realization led, in the 1960s and 1970s, to the development of very long baseline interferometry. In VLBI, radio telescopes on different continents record the signals from the same source at the same time, using atomic clocks so precise that the timing of the recordings can be synchronized to within a fraction of a billionth of a second. The recorded data is then combined by computer, and the interference patterns are extracted. The effective aperture of the resulting instrument is not the diameter of any individual telescope, but the distance between the most widely separated ones. Since the most widely separated radio telescopes on Earth are located on different continents, thousands of miles apart, The effective aperture of a VLBI array is essentially the diameter of the Earth itself, roughly 13,000 kilometers. An instrument of that size, observing at radio wavelengths, can achieve angular resolutions far finer than any optical telescope ever built, sharp enough to read a newspaper headline at the distance of the moon, sharp enough to measure the apparent size of objects billions of light-years away. It was this technique, turned with the full power of an Earth-spanning array toward the ring in Draco, that produced the image in which the pinch was found. The campaign to obtain that image was led by an astronomer named John McKean, working with a team that included Simona Vigeti, the architect of the technique that had first found dark substructure in this system back in 2012, and David Massari, whose expertise in the structure of gravitational systems would prove essential to the analysis. They pointed the global VLBI network at jwst and collected data from radio telescopes spread across multiple continents, each dish recording the same faint radio signal from the ring with atomic clock precision. The signal from the ring is faint. At radio wavelengths, the bent and magnified light of the background galaxy arrives at Earth as a whisper, a signal lost in the thermal noise of the universe. Collecting enough signal to work with required long observations and careful calibration. Combining the data from instruments spread across thousands of miles required computational infrastructure capable of processing enormous quantities of precisely time-stamped recordings and extracting, from the interference patterns they produced, an image of something 10 billion light-years away. The process from observation to final image was not a matter of days. It unfolded over months of processing, checking, calibrating, and rechecking. What it produced was an image of JVASB 1938+666 at a resolution that had never before been achieved for this system. The ring appeared in the final image with a clarity that revealed details invisible in every previous observation. And in that clarity, the ring was not smooth. There, in a specific part of the arc, was the distortion, the pinch, a place where the smooth curve was compressed, deviated from where it should have been if the ring's shape were determined only by the large-scale mass of the foreground galaxy. The deviation was small by everyday standards, but precise enough in this image to be unmistakable. McKean would describe it with the careful understatement of a scientist who understood exactly what he was looking at: a telltale pinch in the gravitational arc. To go from a distortion in a ring to a mass and a position requires a complex chain of modeling. The team had to construct a detailed model of the foreground galaxy's mass distribution, accounting for its shape, its orientation, its known properties. They had to subtract that effect from the ring and isolate the residual distortion, the part that could not be explained by the galaxy alone. From that residual, they had to reconstruct the properties of whatever additional mass was causing it. This required comparing millions of possible configurations, running models, testing them against the data, ruling out alternatives. The process was described by Vigeti as both extremely challenging and incredibly exciting. Challenging because the signal was at the very edge of what the technique could reliably extract. Exciting because it was becoming clear that the residual was real, that it was not noise, not an artifact of the processing, not a systematic error in the calibration. It was a genuine gravitational signal from a genuine object. When the analysis was complete, it produced a number and a structure. The hidden object had a mass of roughly 1 million solar masses. It was located somewhere in or near the foreground galaxy, or along the line of sight, its position constrained by the geometry of the distortion. It was, by a margin of roughly a factor of 100, the lowest mass dark object ever detected at such a distance. It was the most distant object ever detected anywhere in the universe, purely through its gravity. And then the team looked more closely. They asked not just how much mass the object had, but how that mass was arranged inside it. The answer to that question was not what anyone expected. Something about the structure was wrong, and understanding why that wrongness matters requires going back to a question that has haunted physics for nearly a century. Take a moment to sit with the number before moving past it. 1 million solar masses. Our Sun is a star of middling size, neither particularly large nor particularly small by the standards of the galaxy. It contains roughly 330,000 times the mass of the Earth. 1 million suns means 1 million of those, enough mass to form a small galaxy in its own right, to anchor thousands of star systems, to bend the paths of everything within its gravitational reach. A clump of matter that size, sitting at a known position in the sky, should not be easy to miss. And yet every instrument ever pointed at its location has returned the same answer: nothing. Not a faint smudge, not a marginal detection hovering at the threshold of noise. Nothing. The object is dark in every wavelength astronomers know how to measure. Dark in visible light, where ordinary stars shine most brightly. Dark in infrared, where cooler objects and dust glow warmly. Dark in radio waves, where gas clouds broadcast their presence across the cosmos. The most sensitive instruments ever constructed have stared at the position identified by the gravitational measurement and found no evidence that anything is there at all. The only reason we know it exists is the pinch. That small compression in the arc of the Einstein ring, that barely measurable deviation from the smooth curve the foreground galaxy alone would produce. Strip away the ring, remove the background galaxy from the geometry, and the object vanishes entirely. It leaves no trace on any instrument except through the one effect it cannot suppress: gravity. It warps space, it bends light. Everything else it keeps to itself. This total darkness is already extraordinary, but the deeper strangeness lies in the structure. When the team completed the analysis that extracted not just the mass of the hidden object, but the way that mass is distributed within it, the result did not match the catalog of known things. The object's mass is not arranged the way dark matter is supposed to arrange itself. It is not spread out in the gentle, predictable curve that decades of computer simulations have produced for dark matter halos of this size. It is concentrated. Its center is too dense, too compact. A tight core of mass making up roughly a quarter of the total is packed into the heart of this object, with no comfortable explanation in the standard picture of how the universe is built. David Massari described the anomaly precisely. The object is particularly dense at its center, he explained, but that dense center then extends outward to distances far greater than those typically observed in systems of comparable mass. A vast, diffuse shroud surrounding a tight, compact heart. The team summarized the problem in a single sentence. The object is something between an ultra-compact galaxy and a huge dark matter cloud. That description is not a classification, it is the absence of one. The first easy answer, that the object is a faint dwarf galaxy too dim to detect at 10 billion light-years, fails on the light. Even the faintest known galaxies contain stars, and stars radiate. The James Webb Space Telescope, the most sensitive infrared observatory ever built, should be able to detect at least a trace of stellar emission at this distance. So far, it has detected nothing. The dwarf galaxy explanation requires the object to be darker than any galaxy ever observed. The second easy answer, that the object is an ordinary cold dark matter subhalo, fails on the shape. The standard model makes specific, well-tested predictions about the density profiles of dark matter clumps. 1 million solar masses of cold dark matter should not have this much mass packed into its center. It should be far more spread out. The object is too concentrated, too tight at its heart. both easy answers fail. And the object that defeats them both, sitting in complete darkness 10 billion light-years away with a structure that fits no known category, has begun to attract the attention of theorists who suspect it may be the first confirmed example of something the universe contains that our models simply never anticipated. What that something might be becomes clearer when you realize this object is not alone in its strangeness. Because elsewhere in the sky, in other rings, around other lenses, the same anomaly has been found before, and one anomaly can be dismissed. What comes next cannot. Science has a reliable method for absorbing anomalies. A single measurement that defies the prevailing theory can almost always be explained away. Measurement error, calibration bias, a statistical fluctuation that chance has shaped into an outlier. The history of physics is full of anomalies that generated brief excitement before dissolving into noise when better data arrived. This is not a failure of science. It is the process working exactly as it should, applying appropriate skepticism before revising theories built from decades of accumulated evidence. One anomaly is not a crisis. 3 anomalies, found independently in different systems by different teams, using different methods, all pointing in the same direction, is something else entirely. 3 anomalies is a pattern, and a pattern in the behavior of dark matter, reproducible at the frontier of observational capability, demands a response that calibration corrections cannot provide. The object in JVASB 1938 plus 666 has company. The first companion lives in a system called SDSS J0946 plus 1006, known informally as the jackpot lens. The name reflects its improbable geometry, 3 galaxies aligned along the same line of sight, each lensing the one behind it, a nested alignment so statistically unlikely that the astronomers who found it felt genuinely fortunate. Inside the jackpot lens, embedded in the foreground galaxy's halo, there is a dark subhalo detected through its gravitational distortion of the lensing arcs. When its density profile was measured and compared to cold, dark matter predictions, the result was uncomfortable. The subhalo was too concentrated. Multiple independent teams, using different analytical methods and different subsets of the data, have examined it and reached the same conclusion. It deviates from what cold dark matter allows. It is denser than it should be. The second companion is the original 2012 dark clump in JVASB 1938 plus 666 itself. When that clump was re-examined with improved techniques, its density profile told the same story, more concentrated than the standard model predicts. 3 objects, 3 measurements, 3 results pointing identically toward dark matter substructure that is consistently overdense at its center. The cold dark matter model is not a weak theory. It explains the large-scale structure of the universe with remarkable accuracy, correctly predicting the cosmic web of filaments and voids, the properties of the early universe's radiation, and the general relationship between galaxy mass and dark matter halo mass. These are hard-won successes spanning decades of observational tests. But at small scales, where individual clumps can be characterized in detail, the agreement is fraying. The overconcentration found in these lens systems is not simply a minor discrepancy. It is a reproducible signal that the standard theory has no ready explanation for. The most actively discussed alternative is self-interacting dark matter. In the standard picture, dark matter particles are ghostly, feeling only gravity, passing through each other and through ordinary matter, without any other interaction. In self-interacting dark matter, the particles can occasionally collide and exchange energy. Under the right conditions, these collisions cause the core of a halo to lose energy, contract, and collapse inward in a process called gravothermal collapse. The result is exactly the kind of dense, compact core the lens systems reveal. It is a physically motivated and testable explanation, and it would mean dark matter has an internal physics richer than the standard model imagined. A stranger possibility is fuzzy dark matter, also called wave dark matter. In this framework, dark matter consists of particles so extraordinarily light that they behave as quantum waves spread across thousands of light years. These halos do not have particle-like cores. They have solitons, self-sustaining standing waves of dark matter density at their centers, surrounded by diffuse quantum halos. The dense cores in these lens systems bear a structural resemblance to that prediction, and researchers have begun testing whether the details match. And then there is the most dramatic interpretation: a black hole embedded at the center of a dark matter halo. A mass concentration making up a quarter of the object's total, packed into its very center, is consistent with exactly this configuration. A dark matter halo with a black hole for a heart at 10 billion light years, detected by no survey, predicted by no standard model. None of these explanations can be confirmed on current data alone. But 3 systems showing the same anomaly means that whichever explanation proves correct, it must account for a pattern, not an exception. And the test that could begin to break the deadlock between these possibilities requires turning the most powerful space telescope ever built toward the precise position of the object and asking one simple binary question: is there any light there at all? There is a particular kind of suspense unique to science. It is the suspense of a measurement not yet taken, of an answer that already exists in the universe, but has not yet been read. The object in Draco is either luminous at some level that instruments can detect, or it is dark in a way that only gravity can confirm. The universe already knows which. The answer is written in the infrared sky above the position the team has identified. All that remains is the looking. The instrument tasked with that looking is the James Webb Space Telescope. Launched in late 2021 and operational since mid-2022, Webb is the most sensitive infrared observatory ever placed in space. Its primary mirror spans 6.5 meters, more than twice the diameter of Hubble's. It operates at -233 degrees Celsius, shielded from solar heat by a tennis court-sized sun shield. Positioned at a gravitational equilibrium point 1.5 million kilometers from Earth. It was designed specifically to detect the faint, red-shifted light of the earliest galaxies. Objects at distances where even vigorous star formation produces only a whisper of infrared emission by the time it reaches us. The team has a precise sky position for the hidden object, triangulated from the geometry of the gravitational distortion. They are not searching a broad area of sky. They know exactly where to look. A targeted observation of that position, with Webb's full sensitivity applied for sufficient integration time, is the cleanest possible test of whether the object contains any ordinary luminous matter at all. 2 outcomes are possible, and they do not lead to the same universe. If Webb detects faint infrared emission at the predicted position, consistent with a small stellar population at 10 billion light-years, the interpretation shifts toward the familiar. The object would likely be a very low-luminosity dwarf galaxy, unusual in the concentration of its dark matter halo, but made at least partly of stars, fitting awkwardly but plausibly into the existing framework. The mystery softens. The standard picture bends without breaking. If Webb detects nothing, the situation changes entirely. 1 million solar masses of matter at a known position, emitting no infrared light detectable by the most sensitive telescope ever built, cannot plausibly contain stars. Stars radiate. It is what they do. Silence from Webb would mean the object is genuinely and completely dark, composed almost entirely of matter that forms no stars, emits nothing, and participates in none of the ordinary processes of cosmic chemistry. Combined with the anomalously dense structure already measured, That silence would place the object beyond every comfortable category in the astronomical catalog. It would be, in the language the team has carefully chosen, a new class of dark object. In frontier science, finding nothing where something luminous should be is one of the most powerful results possible. It was a version of this silence that first told Zwicky the mass budget of galaxy clusters was wrong. It was the same logic that led Vera Rubin to conclude that spiral galaxies were embedded in invisible mass. The absence of expected light has repeatedly forced the field to confront something real and unaccounted for. If Webb returns silence from Draco, that silence will join that lineage. The stakes become sharper when set against the broader failure of dark matter direct detection. For more than 30 years, physicists have operated increasingly sensitive underground detectors, tanks of ultra-pure liquid xenon, cooled to cryogenic temperatures, shielded by hundreds of meters of rock from cosmic ray background, designed to catch the nuclear recoil of a single dark matter particle. The Earth, moving through the galaxy's dark matter halo, should be passing through a constant wind of these particles. The current generation of detectors is sensitive enough to register interaction rates of less than 1 event per year per ton of detector material. And yet no confirmed dark matter signal has ever been recorded, not one. The gravitational approach does not compete with those experiments. It asks an entirely different question, not whether a dark matter particle can be caught, but what shape dark matter takes when it gathers into a clump. Whether that shape matches the standard theory or demands something richer. The underground detectors have returned decades of silence. The gravitational lenses have returned something stranger, a signal that does not fit. Whatever Webb finds at the position of the object in Draco, the field will not return to where it was before the pinch was found. The question has been sharpened, the measurement has been made, and the instruments needed to pursue the answer at scale are already on their way. A flood of rings is coming. The detection in JVASB 1938 plus 666 was the product of years of work on a single system, instruments pushed to their limits, months of computation, and a chain of inference so carefully constructed that it still carries the honest caveat of frontier science. Real, and not yet fully resolved. The number of systems studied with this level of precision can be counted on 2 hands. Gravitational lensing as a probe of dark matter substructure has, until now, been a discipline of rare individual achievements. That is about to change entirely. The European Space Agency's Euclid telescope, currently mapping the geometry of the dark universe across a vast fraction of the sky, is expected to discover hundreds of thousands of new gravitational lens systems, compared to the few hundred well-characterized today. Each one is a potential probe of dark matter substructure. Each one could harbor its own hidden clumps, its own distortions, its own pinches and rings of ancient light. The square-kilometer array, being built simultaneously across South Africa and Australia, will provide the radio resolution to study these systems in the detail that currently requires painstaking VLBI campaigns on individual targets. Together, these instruments will transform the search for dark matter substructure from a technique of exceptional difficulty into a systematic science of enormous statistical power. The single strange object in Draco is not an endpoint. It is a proof of concept for an era just beginning. What that era touches, whatever answers it produces, is one of the deepest problems in the history of human inquiry. For nearly a century, since Zwicky first noticed that galaxy clusters were moving too fast for their visible mass to hold them, the universe has been known to contain far more matter than we can see. The precise accounting, sharpened by decades of observation and confirmed by the Planck satellite's detailed maps of the early universe, places ordinary matter at roughly 5% of the total mass-energy content of the cosmos. dark matter accounts for approximately 27%. Everything that has ever been observed through a telescope, every star and planet and nebula and galaxy, every photon that has ever reached a human eye or a human instrument represents a minority component, a thin, luminous film on the surface of something vast and dark. For most of the history of the dark matter problem, that vast dark component could only be studied at its surface. Astronomers could measure how much of it there was. They could map where it sat. They could track how it shaped the formation of galaxies and the large-scale structure of the cosmos. But they could not examine a single piece of it in detail and ask what it was made of on the basis of its measured internal structure. The scale was always too large, the measurements always too blunt. The technique that found the object in Draco changes this. By measuring the density profiles of individual dark matter subhalos, astronomers are for the first time doing particle physics with gravitational data. They are asking not just whether dark matter exists, but what kind of thing it is, whether it interacts with itself, whether it behaves like particles or waves, whether it harbors black holes at its center. The deepest question in cosmology is becoming approachable through the shape of invisible clumps at the edge of the observable universe. At the center of this new approach sits a single object, a million solar masses of something completely dark, 10 billion light-years away, its position known, its mass measured, its structure anomalous. It has been there since before the Earth formed, before the Sun ignited, holding its shape in the dark through most of the age of the universe, interacting with nothing except through gravity, unknown and unknowing, one precise cosmic alignment away from permanent invisibility. Consider what it took to find it. A galaxy more than 10 billion years ago sent out light. Some of that light passed a closer galaxy whose gravity bent it into a ring. An invisible object, a million solar masses in size, left a fingerprint on that ring. The light traveled for 10 billion years until it reached a network of radio telescopes on a small planet, combined into an Earth-sized instrument processed by months of computation. And in the final image, a team of scientists read, in the barely perceptible curve of that ancient light, the presence of something the universe had been keeping in the dark. We do not know what it is. We do not know what Webb will find when it stares at its position. We do not know how many more like it are waiting in the hundreds of thousands of rings that the next generation of telescopes will reveal. What we know is that the darkness is not empty. It is structured. It contains things with mass and shape and internal architecture. It is, in its own way, as rich as the luminous universe we have spent centuries mapping. The lights we have always studied are the exception. The darkness is the rule. And somewhere in that darkness, 10 billion light-years away, something with the mass of a million suns casts a small, precise shadow in the light of a distant galaxy. It has been doing so for longer than the Earth has existed. We have only just learned how to read it. The shadow is real. The mystery is real. And for the first time, so is the possibility of an answer.